This R infinity is a space of sequences. It's like A1, A2, da da da, A3, A4, A5, and it just continues without end. That's what R infinity is. And V is a subset where it satisfies that the limit goes to 0. Now, so to show that V is a subspace of R, we're going to use the property that if UV is in V and C is in R, and then U plus CV is in R, is in V. Okay, so that's what we want to prove. Okay. This is our claim. If we prove this, this is equivalent to showing that 0 is in V and is closed under addition and closed under scalar multiplication. So first let's try to see UV in V. What does that mean? That means U is like A1, A2 with limit n going to infinity, AN goes to 0. And V is A1, A2 with limit n going to infinity of Bn. Sorry, I can't use the same A. I should be writing B1, B2. And Bn goes to 0. Okay? So that's what it means. And now let's say W equals to U plus C times V. What does that mean? That means you have A1, A2, da da da, plus C times B1, B2, da da da, right? And that's equal to A1 plus C times B1, A2 plus C times B2, and A3 plus C times B3, and so on and so on, right? Therefore, since limit n going to infinity, let's look at the components of the W. It looks like this, right? It's AN plus C times BN, right? Well, there's a property of limits that says if individually the limits exist, then there's the limit of the sum is same as limit of n going to infinity of AN plus limit of n going to infinity of C times Bn. Okay. Now, if somebody is really rigorous in grading this solution that I'm just writing, I might get points taken off because I can only say that these two are the same if these two are separately finite. But this one I know it's 0, but this one I don't know yet, right? We only know that this is equal to limit n going to infinity of AN, and then C times limit n going to infinity Bn. Okay. So I should really write down this is equal to this first, show that that's 0, and then do this other one. But so I'm being slightly sloppy, but I think this is forgivable. Okay, so this is 0. C times this is 0. So that's 0. Okay. And just to satisfy anyone that's like not liking this solution because I'm being sloppy with the equal signs, I might add like where equality holds because the limits are finite. So I might add this, and hopefully if the very picky grader might read this and say, okay, I'll give you a pass because I said it. All right, but anyways, we got 0, therefore what do we see? We see that indeed that U plus CV is in V. Okay, and that shows that it's a subspace, so that part A is done. Now let's think about this part B, where the question is to show that V is infinite dimensional. Well, how did we show that P of R is infinite dimensional? Do you remember how this was shown? We say this has 1x, x squared, x cubed, and da da da, right? All of these are linearly dependent in here, right? Now the definition of the book on finite dimensional is if there is a finite list that spans this entire thing. But we've proved that if you have a spanning list, then the length of the independent list has to be less than that, right? But we just found infinitely long, I mean, you can grow up to any size, something like this. And this is still linearly dependent in here, right? So no matter what length you say, let's say that there's this length 1 million vectors in here that will span this, then you just have to choose 1,000,001 as linearly independent, and this violates that proof that we had that length of the linearly independent set, independent list has to be less or equal to the spanning list. So there's a contradiction. So we're going to copy that and apply it here almost verbatim. So what we're going to do is, okay, so let me see if you have the intuition. These correspond to what kind of elements in V? Can you guess?
A1 dash A2 and da 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 to the AN. And then condition wise is a limit goes n to infinity, AN equals 0.
So let's say E1 is 1, 0, 0. Now, does this satisfy the condition that the limit goes to 0? Right? It's, if you have zeros every time, then the limit is already 0, right? Okay. So E2. So you just have 1 in the second one and 0 afterwards. What's the limit?
0.
0. Still 0, right? Okay. So keep going. And EK is 0, 0, but you have a 1 at the kth spot. Okay, and then 0 afterwards. Now, then C1 times E1 plus C2 times E2, Cm times Em equals to 0, means you have C1, C2, da da da, Cm, and then 0 afterwards, equals to 0. Right? That's what this is. The C1 times E1 will be C1 comma 0, 0, 0, 0, 0. This one will be 0 comma C2 comma 0, 0, 0, 0, and so on and so on. So if you simplify them and add them, you're going to get this, and that would force C1 equals to C2 equals to everything will be 0. So that says E1 through EM, this list, is linearly independent. For any n. Right? For any n. Okay. So now you prove by contradiction. So suppose V is finite dimensional. Then V is span of V1, Vn for some n. And end V1, Vn. Right? That's the definition. But by the previous, we'll call this lemma, okay? The lemma is that this is linearly independent, okay? Lemma, okay? We have E1, E2, da da da, En plus 1, a linearly independent list that has larger length than n. Okay. And therefore this contradicts the theorem at the end, the theorem that we proved. Do you know what that one is? It's like 2.23. This contradicts.
2.23.
Yeah, 2.23.